So here we go. We're going to do a little lesson on thermochemistry here. We're going to start off with the definition. And thermochemistry is the transfer or the study of the transfer of energy in the form of heat uh, that occurs through chemical reactions or through physical changes. The way we measure this is we use something called a calorimeter. This tool, this calorimeter, is what we're going to use to see if energy is absorbed or released as heat through chemical or physical changes. So here's a simple picture of a calorimeter. And let's go through the parts here. You have this larger container that's going to hold water. It has a stir rod that moves the water around, and it has a thermometer that takes the temperature of the water before and after the chemical reaction or before and or after the physical change. You have these two wires in here that are entering this smaller vessel that's inside of the larger container, and this is where our sample's at. There's oxygen that's mixed in there as well. So if we provide a spark here, kind of like a spark plug, it'll ignite the oxygen that's in there and it'll cause the reaction to occur. And then what happens here is, let's say for example, we're looking at a sample of matter that's in there, and you get the sample of matter to ignite, and it starts to release energy. Well, that water is going to absorb it. So what would happen to our temperature? It would increase. So if the temperature of the water is increasing, that means that it's releasing energy. Remember, we said that the energy releases in the form of heat. And if it's releasing the energy, that means that it's going to be an exothermic reaction. So let's see what the opposite of that would be. It's, simple here. Let's say that the energy is not being released, that the energy is being absorbed. So in that case, then my temperature would start to decrease. And since that energy is being absorbed, that temperature is decreasing. That means that the energy is being absorbed by the environment. So that would be an endothermic reaction. And we talked about endo and exothermic reactions earlier in the year. Sorry, can't get that right. Anyways, endothermic reaction. We could say the same thing for physical changes. For example, if we were melting ice, the ice is going to absorb energy from its surroundings to cause it to melt, to change from a solid to a liquid. That would be an endothermic reaction. If I was going the opposite direction, if I was taking liquid water and I was forming that liquid water into solid ice, that would be the liquid would have to release the energy um, to become a solid. So that would be an exothermic reaction. You can also think of like the movement of particles, which movement of particles are moving faster, right? For different states of matter. So that's a calorimeter there. Just going through it with you and covering the basics of it. So looking at temperature, temperature is the average kinetic energy of particles. And so if I take a look at the particles that are inside this container right here, um, if I wanted to measure their temperature, then I would have to take an average of all of the movement of all the particles that are hitting this thermometer over here. And that average kinetic energy for all the particles, that would give me a temperature. So if I were to increase the temperature here by adding heat, you can see that the particles are going to move faster, so they're going to have a higher temperature because now the average movement of all the particles, it's much faster. If I were to cool them down, you'll see that the thermometer temperature drops, right? So there's less interaction of these particles that are hitting the thermometer, causing the temperature to drop. So that's what temperature is. It's just a measure of the average kinetic energy of the moving particles. We measure the temperature in 2 units. So you'll see Celsius, and they usually put a degree Celsius. So you have this little zero up here. It looks like a zero up there on the top, and that's degrees. And then you're followed by a capital C, Celsius. And Kelvin is just a K, right? How do we measure how much heat is being either absorbed or released through a chemical reaction or a physical change? Well, we measure that in a joule, right? That's how energy is measured. So moving on to the next slide. When we talk about energy in the form of heat, we have this symbol that's given to heat. which is Q. So Q is going to represent the heat in the right, that type of energy that's being transferred between two samples of matter because of a difference in temperature. So if there are different temperatures, it's always going to move spontaneously from the higher temperature down to the lower temperature. And I have just a simple example here with these two blocks. And let's just say that this was block number 1, and the darker one is block number 2. Let's say that block 1 is at 100 degrees Celsius. Block 2 is at 0 degrees Celsius. You can see that block 1 is much higher in its temperature than block 2. And let's say I'm going to put these two close together to where they're side by side. Because block 1 has a higher temperature, it's going to transfer its energy spontaneously over to block 2 until they are the same temp. So let's just keep this simple. Let's say we put them together and I see that block 1 and block 2 are the same temperature at 50 degrees Celsius. That means that at that time, the spontaneous movement of the heat energy is going to stop. There's no more heat energy that's going to be transferred between the two blocks because they're the same temperature. Same thing happens with the calorimeter. You know, once the water and the energy being released from the chemical reaction or the physical change are equivalent, then that energy, um, that transfer of energy stops, just like we saw with the blocks. So that's what this slide is talking about right here, what I just covered with the blocks. Down in this slide right here, going back up again, we see that there's an equation that we can use to measure for the heat energy, or let's just say we're giving the other three variables. Let's say we're given the mass, the energy, and the temperature, then we can solve for specific heat. So I'm going to stick to problems that either solve for the energy or that solve for the specific heat, just to keep things kind of simple for us. So let's talk about what specific heat is. If I have a sample of matter and I want to know how much energy in the form of heat is required to change 1 gram of that matter by 1 degree Celsius or Kelvin, then that measurement would be specific heat. For our purposes, specific heats have already been predetermined. You can usually find them in your textbook, you can find them in a reference book, or you can find them online. What's useful for us is water. Water has a very high specific heat, and it's a very versatile substance, so we can use it to cool down nuclear reactors, we can use it to cool down cars, we use it to cool down our bodies. The environment uses it to keep the weather and the temperature in check, right? So it's a very, 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 very useful substance for us because it has a pretty high specific heat, right? To change the 1 gram of water by a Kelvin, it would require 4.18 joules of energy. So at this point, what I'm going to do is I'm going to switch over and I'm going to show you how to work about 3 problems. Two of the problems are this right here, and then I'm going to do one other problem that I picked off of a different worksheet. Okay, so here's the first problem. You'll notice that I wrote the equation out from the slide. Q is equal to M times the specific heat times the change in temperature. And here they're giving me heat, so they're giving me the value of Q. The value of Q is, excuse me, over here down at the bottom. I have circled the wrong one. Looking for a unit of joules whenever I'm talking about heat or energy. So that should be 32 joules. Let me see if I can write this correctly. So 32 joules of energy is what was added to a 4 gram. So here's my mass. 4 gram sample of glass. And the glass was at a temperature of 274, but now it's at a temperature of 314. So here this delta T means that I need to take my final temperature and subtract it by my initial temperature. And that gives me a value of 40. So what I'm looking for is the specific heat. So plugging these values into the equation, Q is 32, M is 4, Cp is my unknown, which is X, and my change in temperature is 40. So now what I'm going to do, simplify the equation. So 4 times 40 is 160, and then simplify it one more time, and I'm going to get a specific heat of 0.2. None of these units cancel out, so I'm going to be left with joules divided by grams Kelvin. You'll notice that I kept one significant figure for the mass. So that was problem number one. It took, it was the specific heat of this particular sample of glass turned out to be 0.2 based off of the amount of the mass of the glass, the difference in temperature, and the amount of energy that was added. Part two of that problem um, is now asking me to determine the amount of energy. So that's my unknown. This time is going to be Q. And remember that energy is measured in joules. When they raise the temperature of the glass from 314 to 344, so now 344 Kelvin is my final temperature. I need to subtract that by 314 so I can get this thing right. Sorry about that. That's going to give me the other pen's kind of acting up on me here. That's going to give me 30 Kelvin. Temperature difference, and we just solved for the specific heat and the problem above, which was 0.2 joules a gram Kelvin, and then the sample of glass is still the same mass. So now I'm going to plug this into my equation. This time I'm solving for Q. So I'm going to take 4 times 0.2 times 30. Oh, excuse me. Yeah, that's right, 30. And I'm going to get, when I multiply these all the way through, I get 24, but keeping my significant figures, I'm going to round that to 20. So here the units do cancel out and I'm left with joules. So here grams cancels grams, Kelvin cancels Kelvin. I'm left with joules for the amount of energy. So this is the amount of energy that has to be absorbed by this mass of glass at that difference in temperature with that specific heat. Okay, so this one I kind of already set it up since we've already worked out two problems just to make it a little bit faster. Again, I'm looking for the amount of energy. So I've already got all the variables set up and written out. So X is equal to 100 times 4.18 times 33. And this time the value for X, taking into account significant figures, is going to be 13,790 joules of energy. So again, Celsius cancels Celsius, gram cancels gram. And that's it for this particular lesson.